All right, welcome back to the last part of chapter number 10, looking at Lewis structures. Like I said, I went ahead and broke it up into three different parts because this last part, I just want to kind of maybe go a little bit slower, not necessarily too slow, but just a little bit slower through it because we're going to talk about topics that we're going to have to really think about logically and how to solve some of these problems and do some of these things. And so I really just wanted to take the time to kind of slowly, not necessarily slowly, but just again give it the full amount that it would need. And so one of the things that we talked about, we finished up last time, was that whenever we draw Lewis structures, we always kind of depict them as static things, right? Oh, here's the structure, this is it, electrons stay there. When in actuality, these electrons, especially in a covalent bond, are constantly moving, right? They're constantly shifting, they can change. And what this leads to is what's known as resonance. And that what you have is one or two or more Lewis structures that can have the same skeletal formula, but different electron arrangements. And here we're looking at ozone or O3, right? As you can see that there's three oxygens bonded the same way, or structural the same way, but they're just different bondings between, right? The double bond on the one on the left is on the left, and the one on the right, as you're looking at the screen, is on the right, right? And so those are different. Technically, those are different. And the way we can depict them is through a hybrid structure. Just like, with the dogs, right? You can put two dogs together, get a hybrid structure. You can put two Lewis structures together and get a hybrid. We're not going to really deal with the hybrid structure, but let's go ahead and look at an example of this. And then we're going to talk about how we know which one is more quote unquote correct, right? Because just because we see two or three different resonance structures, one of them is more correct than the other, possibly. Of course, in the example that we're going to look at with NO3, there's actually not exactly and necessarily one correct one, quote unquote. So let's go ahead and we'll do this one, and then I'm going to we'll do NO3 real quick, and then I'll show you another one. Or actually, I'm going to do this, just because this will be a better example. I want you to do NO3. I want you to do NO3 minus 1. But what I'm going to show you, though, first is how we can calculate valence electrons, especially when we're looking at a polyatomic ion, right? So again, if we're looking at a polyatomic ion, then the overall charge of the molecule has to be in -1. I'm just going to go ahead and do it. Nitrogen, there's 5 of them. Oxygen, there's 3. We said oxygen is 6 times 3 is going to be 18. So total valence electrons are going to be 23 as just NO3. But what is NO3, right? It's a -1. And so if we have a -1, we need to add another electron. So we now have 24 total electrons. Which molecule or which element is going to be in the middle? Exactly. Nitrogen is, because it is the least electronegative, right? And so then we just fill in everyone around it. I'm going to go ahead and just draw the bonds as lines. Remember, each line is worth 2 electrons. Turn on the blue here. Each bond is worth 2 electrons. So 2, 4, 6. So we have 18 electrons left. So we start filling in. Oh, look, 6, 12, 18. Sweet, I am done, right? Nope, not done yet, right? Because this nitrogen does not have an octet. Okay, so where, and this is where we can see resonance. Where do you want to make the double bond from? Right? Because it's really your choice. Let's start over here. So then we would have O double bond, N bond O, bond O. Now, it's very important when we talk about things that have a negative charge, right? When we talk about polyatomic ions, there's 2 ways to depict a polyatomic ion. And this is the easiest one, right? Is that this whole structure is a -1 charge. Okay? So that's how this would, but you can see though, is let's say we decided not to do it there, but we did it there. Or let's say you didn't want to do it there. You wanted to do it there, right? All of those are the same pretty much. They're different structurals, but they look exactly the same, right? That it's an N double bonded to an O with single bonds to other oxygens. Right, in the middle has an octet. So everything is fine. This is a perfectly valid Lewis structure. On an exam or on a quiz, if I were to say, draw this Lewis structure for NO3, either all three of them would be correct if I don't specify which one I want. So let's go back, though, because that's an example where all the resonance structures are exactly the same. Right, let's go back to this one, N2O. Right, this is nitrous. If you've ever been to the dentist and they gave you laughing gas, this is the laughing gas. And so 2 nitrogens, so 5 times 2 is 10. We said oxygen is 6. So there's 16 total electrons. So there's 2 nitrogens. One of them will be in the middle, and we'll just do them like this. So here's the single, minus 4, we have 12. You can kind of, so right, I'm moving kind of quickly just so that we can, get it done. You can slow down the video. If you have any questions, again, feel free to ask me, please. So what do we say? The middle one does not have an octet, right? So we can do double bonds. So I'm going to do resonance structure number 1 is this. Right? Resonance structure number 1 is that. Resonance structure number 2 is going to be this. So I'm going to drop this in here. I'm going to take this away. So I'm going to make a triple bond, right? Because remember, you can make a triple bond between 2 different atoms in a molecule. So there's 1, there's 2, and then if we just switched it and made the triple bond between the oxygen and left the nitrogen singly bonded, there's number 3. So I want you to look at these 3, and I want you to tell me, without me teaching you anything about how to do it, I want you to tell me which one is correct. 1, 2, or 3. Okay, now let me tell you how we can tell which one is correct. So we're going to tell you which one is correct in just a second. Because there are rules to this. Again, more rules. Woo, more rules. All right. So formal charge, that's what we need to calculate. And the charge, and what formal charge is it's the charge if it would have all of the bonding electrons were shared equally between bonded atoms. What I mean by this is, what you're going to do is you're going to count how many electrons are around each individual atom of a molecule as you construct it with the Lewis model. And then what you're going to do is you're going to compare it to valence electrons. And if there is a difference, whether it would cause something to be positive or something to be negative, that is that atom's formal charge. Sum of all formal charges of a neutral molecule must be 0, right? So in this case, we look at N2O, all the formal charges should equal to 0 because the overall charge on the molecule is 0. The sum of all formal charges in an ion must equal the charge to an ion. So if you were to go back to our NO3, and I would recommend you doing this to calculate the formal charges, you will find that the formal charge will always be -1. There will always be a -1 left over, and that's okay because it is an ion with a -1 charge. Small or 0 formal charges are always what we want. Right? You could possibly make a Lewis structure with you get a -5 and a +4 to get that -1. That is not ideal. And what we actually want is to get as small formal charges as possible. When formal charges cannot be avoided, right? When we have to put formal charges, we'll see that in this example. When you have to put a formal charge, negative formal charges should always try to be put to the best of your ability on the most electronegative atom. So in this case with nitrogen and oxygen, we'll see as an example, we want to put the negative charge on the oxygen more than what we want to put it on the nitrogen. All right, so let's go back to the board and let's calculate some formal charges. Okay, so we said nitrogen has 5 valence electrons. That's the number we're going to compare it to. Oxygen has 6. That's the number we're going to compare it to. So we have 5 and 6. So how many electrons? Because remember, each bonding pair, I'm just going to do it on this side. we can think of it like this. And when we think of it like this, we just split it down the middle. So this nitrogen for number 1 has 1, 2, 3, 4, 5, 6, has 6. Normally nitrogen has 5 valence electrons. So it has one extra one, which means it's going to be a -1 charge. This nitrogen has 1, 2, 3, 4. Normally it has 5, so it's lacking 1. So this is going to be a +1. This oxygen has 1, 2, 3, 4, 5, 6. It's not going to have any formal charge because its valence electrons equal the number of lone pairs and bonding electrons that it has in this Lewis structure. Let's go to number 3. We'll calculate number 3. So there's 1, 2, 3, 4, 5, 6, 7. So there's 7 electrons around that nitrogen. Nitrogen normally has 5, so that's going to be a -2. This nitrogen still has 4, right? 1, 2, 3, 4. So it's still going to be +1. This oxygen, 1, 2, 3, 4, 5, has 5, which is going to be a +1, right? Because it normally has 6. Let's look at this one. 1, 2, 3, 4, 5, no charge. 1, 2, 3, 4, +1 charge. So you're going to start seeing a pattern. That middle nitrogen, right, is always going to be +1. So that tells us we cannot avoid having, at least something has to be charged. We can't have all zeros like we would want. Now we have 2, 4, 6, 7. That's -1. Okay, so based on these numbers and just trying to quickly remember the rules that we said in the slide, which one can we easily get rid of? That's right, number 3. We can get easily rid of number 3 for 2 reasons. One, everything has a charge, and we have the biggest charge of -2, and we don't want big charges. And the other one is that oxygen has a +1. Oxygen is pretty highly electronegative. It does not want to be positive. So we can get rid of that one. All right, so now, with that being said about our electronegative oxygen, which one of either 1 or 2 is going to be the one that we want? Exactly. Number 2 is going to be the more likely resonance structure found in nature. And because the negative charge is on the oxygen, the more electronegative atom. The thing is that, all 3 are found in nature. Obviously, number 2 will be found more often than number 1 and number 3. But that's just something that we need. So that is resonance, right? That these electrons can move and can be shared a little bit differently than what we just post on the board. Okay, there are exceptions to the Lewis octet rules, right? We need octets, except for if we have odd electron species like NO2, not N2O, but NO2. You can see that lone one single electron above the nitrogen in the middle. That is known as a free radical. Free radicals are actually damaging, and they damage our skin and they damage our bodies. They're thought to be what leads to aging. And so free radicals, I will try to prevent you from having to do free radical, right? That free radical, just because it's weird chemistry. When you do organic, if you have to take organic chemistry, you will see free radicals. And the chemistry of free radicals, they don't last very long in nature. Let's talk about incomplete octets. Boron has an incomplete boron trifluoride. You're given the Lewis structure here. Boron does not have a complete octet. I would like you guys to see why, right? Why that it's okay for boron to have an incomplete octet, especially for BF3. I would like you to try to make one of those a double bond and then calculate formal charges. And you're going to see something interesting with fluorine. Remember, fluorine is the most electronegative element in the periodic table. And something happens that's very, very unstable or unfavorable. The last thing is that we can do what's known as expanded octets. Sulfur, arsenic, iodine can expand their octets above the 8 into a 10. And the question is why, right? Because what we see with expanded octets, and this is very important, is sulfur can do it, phosphorus can do it, arsenic can do it, iodine can do it, bromine can do it, xenon can do it. What do all these things have in common is that they're found in row number 3, right? They're found in row number 3. What these have that other things don't have is that they have an unused d orbital. We'll talk about this in the next chapter. But what happens is they have unused d orbitals that they can put electrons in, that they can expand their octets. And so I would like you guys to try to draw the two compounds, iodine pentachloride, so ICl5, and then this SO4 minus 2, so sulfate is SO4 minus 2. I want you guys to try to draw those Lewis structures. If you want me to check them, that would be great. But those two things have expanded octets, and I would like you just to try to draw it. It'll be weird because you have to do more than 8, but I just want you to try it. So here's in one more way. So we looked at 3 ways to calculate delta H: through a calorimeter, through Hess's law, and through standard formation. Here, what we're going to use is we're going to use bond energies to calculate the enthalpy changes of a reaction. So we can calculate delta H of the reaction through the breaking and the reformation of a bond. We can use the average bond energies to estimate the enthalpy changes, right? This is not going to be exact. This is just an estimate. Delta H, again, we don't really care about the exact numbers. We just care about the ranges. We can see what enthalpy will be based on the strength of the bonds broken or formed. What do I mean by that? Here's the equation. The equation is delta H of the reaction is equal to the sum of the bonds broken plus the bonds formed. Bonds formed will always be a negative number because we're forming bonds, we're releasing energy. When we release energy, that number is negative. Bonds broken always take energy to be broken. That number will always be positive. If you break stronger bonds than you form, you will have an endothermic reaction, right? Because your number will be positive. If you form stronger bonds than you break, your delta H of the reaction will be exothermic. It will be exothermic, right? And there is a correlation between bonds broken and energy released and energy formed. Not only does that matter, right? And this is why we're covering this in this section, is because we kind of have to know how things look, which bonds break, which bonds form, to actually calculate this. And so teaching this any earlier with the thermochemistry chapter, we would then have to cover chapter 10. The average length of the bond, right? So single bonds are longer than triple bonds. So obviously something that's shorter, something that's stronger will take more energy to break. And so a single bond is easier to break than a double bond. So let's go to the board and let's look at this in action. And then this will end chapter 9, or chapter 10, excuse me. And actually, trying to remember, I don't think there is much, if at all, any math in chapter 11. I think chapter 11 is all conceptual. And so that is a great thing. So let's go ahead and look. So CH4 gas plus 2 H2O gas yields 4 H2 gas plus CO2 gas, right? So we're forming hydrogen gas. I'm going to tilt this up. Okay. So now let's think about this, right? Because what we're doing over here, we're going to break bonds over here. We're going to form bonds over here, right? And so we know the sum of the bonds broken minus or plus, it'll be the sum of the bonds formed, but this will always be a negative number, right? So this is always positive, this is always negative, will give us the delta H of the reaction. So what does CH4 look like? It's going to look like this. So how many CH bonds are we going to break here? Well, we don't have any CH bonds over here. So we're going to break all 4 of them, right? And so what we're going to do is we're going to take 4 times the energy of that CH bond. We're going to add it. So here is water, H2O, O in the middle, H coming down, right? So how many bonds are we going to break for H2O? Exactly, we're going to break 2 bonds. But wait, how many moles of water do we have in this reaction? We have 2 moles of water, so 2 moles. So 2 times 2 bonds breaking is going to be 4 of these bonds breaking. And so what I normally do is just do minus, because that way, it's going to be a negative number. It just helps me keep that negative number. So what's hydrogen? Hydrogen is this, just H bond H. There's 4 of them. So 4 H bond H minus, remember, carbon dioxide is this, C double bond O with the C double bond O. And so there's 2 C double bond O bonds. Okay? So I want you guys to go to the table, look up the energy of these bonds, plug in the numbers, and calculate the delta H of the reaction. And I also want you guys to predict, just by looking at it, doing a brief prediction, like, oh, look, these are the bond strengths. I want you guys to do just a quick prediction on whether this will be endothermic or exothermic, because that will help us check our answers. So this ends chapter 10. This ends Lewis structures. We are now going to get into chapter number 11, and then we'll be done with semester number 1.